I'm and welcome to my lecture series on computer and network security. In this video on symmetric ciphers, I will talk about stream ciphers. Stream ciphers are a type of symmetric cipher that encrypts element per element. An element could be a bit, a byte, or a letter in the alphabet. We've already seen some examples of stream ciphers in previous videos. We've talked about the Vigenère cipher, which encrypts letter per letter, or the one-time pad, which encrypts bit per bit. One characteristic of these two ciphers is that each bit or element in the plain text needs to be encrypted using a corresponding element in the key. Therefore, we need a key stream that's the same length as our plain text message. In Vigenère, this is obtained by repeating the key over and over again, while in the case of the one-time pad, the key actually has the same length as the message. We have shown that repeating the key over and over again is insecure, while having a key of the same length as the message is impractical. Stream ciphers try to solve this problem, and they are a practical version of the one-time pad. The main idea is to replace the random key by a pseudo-random key. This is done using a pseudo-random generator, or PRG, that turns a key seed into a pseudo-random bit stream. As such, we transform our key of length s, so as bits, into a pseudo-random bit stream of n bits, where n is the same size as our plain text. And here you see the resulting encryption system. So we have the same general principle as the one-time pad, where we combine each symbol, for example a bit, of our input plain text using an exclusive OR operation with the corresponding element of our key. But in this case, the key is pseudo-randomly generated from a key seed. As such, stream ciphers require one of these pseudo-random stream generators. I have a question for you related to this. Can a stream cipher be unconditionally secure, like the one-time pad? Possible answers are yes, if the PRG is secure, yes, independently of the PRG, or no, it cannot be unconditionally secure. Feel free to pause the video while you think about the answer. And in a second, we'll take a look at the correct one. So let's take a look at the correct answer. And the correct answer is 3. No, it cannot be unconditionally secure. I've already given you the answer to this question during the previous video on the one-time pad, because to be unconditionally secure, there were two requirements for the one-time pad. First, there cannot be reuse of the key, so the same key cannot be used to encrypt two messages. And second, the key length has to be equal to the message length. This is not the case for stream ciphers because the key is shorter and the generated key stream is only pseudo-randomly generated, and it depends on this shorter key. Now, a stream cipher can be computationally secure by making the PRG unpredictable. And we define unpredictability based first on the definition of predictability. So let's first define what predictable means. We say that a PRG G is predictable if there exists an efficient algorithm that, given the first I bits of this pseudo-randomly generated key stream, is able to predict the next bit I plus 1 in a non-negligible probability epsilon. So what does this mean, and how can we exploit this? It basically means that if we can obtain some parts of this key stream K, GK, we are able to predict the next bit. And obviously, if we can predict the next bit, then based on that, we can also predict the bit after that, and so on. How can this be exploited? Well, you see that here in this figure. Let's say we have a ciphertext C, and our cryptanalyst is able to intercept, or attacker is able to intercept the ciphertext C. Now let's say he doesn't know the original plain text message M, but he does know some kind of header at the beginning of the message. Let's take, for example, an HTTP message. In that case, the attacker may be able to predict what is the header of this HTTP message. Using the XOR operation, the attacker can derive, using this known header, parts of GK, namely the first part, because the properties of the XOR operation allow us to retrieve the key from the ciphertext and the plaintext. If our PRG is predictable, then based on these initial bits of GK, our attacker will be able to predict the next bits. Maybe bit per bit, but based on that he will be able to derive the unknown part of GK. And a PRG is unpredictable, obviously, if it is not predictable. So based on this definition of predictability, we can also define unpredictability. And let's take a look at a few existing practically used stream ciphers. And the first widely used stream cipher was RC4. You've probably heard of RC4. It's a very known stream cipher. It's been widely used in different kinds of encryption algorithms and protocols. And it was designed by Ron Rivest in 1987. The name may ring a bell because he's also one of the inventors of the RSA algorithm, which is an asymmetric encryption algorithm, which we will talk about in future lectures. So it's a variable key size stream cipher with byte-oriented operations. That means it doesn't encrypt bit per bit, but it works on bytes, so groups of 8 bits. And it was widely used in WEP encryption, which is the encryption protocol used for Wi-Fi in the past, but was found to be insecure there, not because of RC4 itself, but because of the key being incorrectly generated. It's still an optional feature in WPA and SSH. So WPA is the successor of WEP for Wi-Fi security. However, recently, 2015, more vulnerabilities in RC4 were exposed, and it's now prohibited for use in TLS, transport layer security. So RC4 is no longer advised to be used, so I won't go into detail about how RC4 works exactly. Instead, I'll talk about another stream cipher that is now becoming more popular because it is considered secure at this moment and no known attacks exist against it. And its name is Salsa20. It was designed by Daniel J. Burstein in 2005. And there's also a modified version that's also widely used called Chacha, which was published in 2008. Chacha improves on Salsa by improving the round function and increasing the performance, computational performance on some hardware architectures. Chacha is also published as an IETF RFC under the number 7539. And Salsa basically defines the pseudo-random generator function that should be used to generate the key stream based on the key. The rest of the operations are the same as in the runtime pad, so it combines this key stream with the plaintext using the XOR operation. And the pseudo-random generator function of Salsa is based on the principle of add, rotate, XOR or ARX. And this means that it uses 3 operations, namely addition, modulo 32 or 2 to the 32nd, bitwise addition, so the XOR operation, and a fixed binary rotation, so that's a circular bit shift. As inputs, it takes a key of 256 bits. Also, a 128-bit key can be used, but obviously this is less secure. A nonce of 64 bits. The nonce is a unique pseudo-randomly generated number that changes every time the function is called. And a counter value, also 64 bits, that is increased by 1 for every execution of the pseudo-random generator. So why does it use this ARX principle? This ARX principle, so add, rotate, XOR, has several advantages, and many ciphers therefore use it. First of all, it relies on 3 basic operations, which I already explained on the previous slide. And the reason it uses these 3 operations is because they are computationally efficient to execute both in hardware and in software. Also, very important, they run in constant time. For example, modular exponentiation or modular multiplication don't run in constant time. And the reason why this is important is to avoid timing attacks. Specifically, attackers can use the time it takes to execute a certain operation to decrypt messages. I will talk more about timing attacks in later lectures on asymmetric encryption, where they are also used to decrypt messages by attackers. But these 3 operations run always in constant time, and therefore they are not vulnerable to this type of attack. So let's take a closer look at the PRG of SALSA20. Specifically, it transforms the key, which is 256 bits, and the nonce R, which is 64 bits, into a key stream of the same length as the plaintext message, so length n. And for this it uses a so-called expansion function h. So this function takes as input our key, our nonce, and position counter p. So how do we create this pseudo-random key stream? Well, we just execute the function h over and over with the same key and nonce, but with a different counter, and we put these together until the desired length is reached. So the counter is increased every time the function is called. And each time the expansion function h is executed, it generates a single 64-byte key block. This key block is represented as a 4x4 matrix. Each element in this matrix is a word consisting of 4 bytes. The function h takes as input, as I said before, the key k, the nonce r, and the position counter p. These are used to generate the initial state. This initial state is then transformed using the function f into an intermediary state. This process is repeated 10 times, and after 10 times the output is summed word by word with the initial state, and this generates the output of this function h. As I said, to generate the key stream, this entire process is repeated until enough 64-byte key blocks have been generated for the key stream to be the same size as the input plaintext. Every time it is executed, k and r remain the same, but c will change. And as I said, the PRG, while generating key blocks, uses an internal state in the form of a 4x4 matrix. This 4x4 matrix consists of 16 words, each 4 bytes in length. And here you see how the initial state is created. So it consists of 4 different types of information. First is the constant C. So the constant is the same every time the algorithm is executed. It is an ASCII. It takes the form of 16 ASCII symbols that read expand 32-byte K. Next is our key K. K is normally 256 bytes, so it is split into blocks of 4 bytes, 8 blocks of 4 bytes that are positioned here, 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 and here. If the key is only 128 bits, then block 5, 6, 7, and 8 are just repetitions of block 1, 2, 3, and 4. This makes the algorithm, as mentioned, less secure. Next up is the nonce. So the nonce is a pseudo-randomly generated number that is different for each message that is encrypted. So for a single message, the function h is executed multiple times, and then the nonce stays the same. However, every time the function is executed, the position counter p does increase by 1. So the output will be different every time. This position counter p is reset to 0, starts at 0 and then is increased by 1 at every execution, as I mentioned. And to see if this is clear for everyone, I have an exercise for you that you can solve on your own. So the question is, calculate the initial 4x4 64-byte state given the following 28-bit key K, 64-bit nonce N, and position P. Note that in the given inputs, the key and the nonce are written in hexadecimal format, while the position is written in decimal format. Goal of the exercise is for you to calculate the 4x4 initial state. And let's talk in a bit more detail about the round function. This round function is used, repeated 10 times in a row on each initial key block to generate the output block. And the round function applies the quarter round function QR twice in each round. In total, QR is thus applied 20 times, 2 times each in 10 rounds. The QR function takes a forward input, so those are forwards at a time, to generate forward output. QR is first applied column per column on the input state Si, and then it is applied row per row. These are referred to as the column round function and the row round function. How does it work? So first, at the out executions of the round, we apply QR column per column, so that means word 0, word 4, word 8, and word 12 are given as input to QR, and this generates a new word 0, 4, 8, 12. Same is done for the second column, the third column, and the fourth column. Next is the row round function, which repeats this, but per row. So first, QR is applied to word 0, 1, 2, and 3, and the same for the second row, the third row, and the fourth row. Finally, the output of this becomes our next state Si+1. You don't need to know the details of the quarter round function QR, but let me give it for completeness. So as I mentioned, it uses the ARX principle. So that means it uses modular addition, circular bit shift, and XOR. Each of the 4 input words is used to generate 4 output words. The way this is done, like this, avoids the need for additional memory, as first y1 is calculated, then y2, y3 and y0 by every time updating, in this case x1, x2, x3, x0, and the original x1 does not need to be kept in memory when calculating the new x2, y2 and so on. So the operations are the bitwise exclusive OR, word by word addition modulo 2 to the 32nd, and a binary left rotation, so circular bit shift. This basically means, for example, in the first case, that the first 7 bits, leftmost bits, are taken and put on the right of the word. Cut. So this means that all the bits are shifted, in this case 7 positions to the left. If a bit falls off on the left, it is moved to the right of the word. To make sure everyone understands how the QR function works, I have an exercise for you. So given our 4 32-bit words, x0, x1, x2 and x3, calculate QR of x0, x1, x2 and x3. So these are the 4 words. In hexadecimal format, you should determine y0, y1, y2 and y3. And let's end this video with looking at one of the most important pitfalls of stream ciphers. I already mentioned that this should be avoided when talking about the one-time pad, and it is key reuse. When using stream ciphers, you should never reuse a key more than once, meaning you should never use a key to encrypt more than a single message. Why is this? Well, let me show you how this could be used by an attacker to derive information about plain texts. So let's say you have 2 ciphertexts, C1 and C2, that have been encrypted using the same key. So the key has been used twice as input for the pseudo-random generator function for 2 different messages, M1 and M2. An eavesdropper could overhear the 2 ciphertexts and retrieve them. Using this, he can also obtain information about the plain texts, even if he doesn't know them or knows the keys. Because due to the properties of the exclusive OR, by XORing C1 and C2, he knows that this is equal to the exclusive OR of M1 and M2. And due to the frequency information that's embedded into modern languages, if M1 and M2 are written in some spoken modern language, then there is enough redundancy to allow retrieval of the plain texts based on this information. And Salsa does not force you to generate a new key for every message M that is encrypted. However, it does generate new nonce. And by using the key and the nonce as a unique combination, the key itself can be reused as long as the nonce is different every time. That was it about stream ciphers. In the next video I will talk about the general block cipher structure. Block ciphers are an alternative way of doing symmetric encryption.